Reza Gheissari from UC Berkeley, and he's going to talk about cutoff for Glauber dynamics of the discrete Gaussian field. Thank you, Reza.
Thanks for the invitation to speak. So yeah, I'm going to be talking about recent joint work with Shirshendu Ganguly, who's also at UC Berkeley, on dynamics for the Gaussian free field. So let me remind people what the discrete Gaussian free field is. So the underlying geometry we're going to be considering is an n by n by n cube in ZD is as an index set. So I'm going to use lambda n to denote that. And so here's lambda n in dimension 1 and lambda n in dimension 2, for instance. And the discrete Gaussian free field is going to be an instance or a random height function, which is an assignment of heights to the points of lambda n. So for above each point, we assign a height. And I'm going to assume this boundary data that the height function that I'm looking at has value 0 all along the boundary. And so the boundary is, here, here. Okay, so we get a random discrete surface or height function. And the distribution of this function is going to be a Gaussian process with mean 0, whose covariance is given by the Green's function. So the Green's function, I'll remind everyone, is you run a simple random walk yk and you start it at x, so this is gxy, and you count the number of times that it visits the site y. Okay, so the covariance between the height at x and the height at y is the number of visits from the random walk started at x to the site y before hitting the boundary partial lambda n. Okay, so once we hit the boundary, we stay at the boundary forever. We're frozen there and we don't move anymore. An alternative formulation of this that maybe is a little more familiar. Well, so first, sorry, before I get there, just to remind people, the Green's function in dimension 1 is of order n. So this gives you essentially a random walk bridge. So you have the usual diffusive scaling, so the variance is order n. In dimension 2, the Green's function is, well, so gxx is log n, and it decays as log n over x minus, over the distance x minus y. And in dimension at least 3, it decays as the distance to the 2 minus d. Okay, so what you should think about here is just that in dimension 2, you have a random surface with log n variance and also log correlations. So this is a log correlated field. And in dimension at least 3, you have a kind of rigid random surface which has order 1 height fluctuations and has rapidly decaying correlations, polynomially decaying correlations. So here's just a picture of a Gaussian free field instance in dimension 2 and in dimension 1. And what I'm saying is this height is roughly square root n, whereas this height is roughly log n. Okay. Another formulation of this same process is as a Gibbs distribution over height functions. And you have this kind of Dirichlet energy term. So we're summing up over all neighboring vertices the gradient in the height along the difference of the 2 vertices. Okay, so you look at the difference, you square the difference of the heights at 2 neighboring vertices, and this gives you the energy of a random surface, and you have a Gibbs distribution over such random surfaces. One can check that these two are the same random surface model. Okay, so that's the discrete Gaussian free field. And what we're interested in is some form of dynamics for this model whose stationary measure is the distribution itself. So a natural choice of this is what's called the Glauber dynamics. So for me, the Glauber dynamics for the free field is going to be the following process, and we're working in continuous time. So it's a continuous time Markov process over these height functions that always have boundary data 0, where I initialize from some initial profile h of 0, and then I assign each vertex v in lambda n a rate 1 Poisson clock. Now, whenever the clock at a site rings, I'll update the value of the height function at that site. And the update I'll do is I'll take the average of its neighbors, and then I'll just add an independent standard Gaussian to it. Okay. So this, if you have maybe 4 neighbors, these are your 4 neighbors, and you're looking at, this is the vertex in the middle, and its height is atypically large, the effect it's going to have is you're going to take the average of them and add some standard Gaussian, and basically it smoothens the surface and then it adds some stochasticity to it. Okay. So this is a Markov process, and as I said, it's easy to check that the stationary distribution of this Markov process is the discrete Gaussian free field itself. And so if you run it for a sufficiently long time, you see that the surface, no matter what the initial height profile is, will converge to the discrete Gaussian free field distribution. Okay. Just for a bit of context, one can see a relationship between this process and then continuum stochastic partial differential equation, which is, maybe the first SPDE that one thinks about, which is the stochastic heat equation with additive noise. And so the relation here is, so the stochastic heat equation with additive noise is the stochastic PDE that says that the time derivative of the surface is given to you by the Laplacian in space, plus this is just a space-time white noise. Okay, so if we look back to the last slide, you had this averaging effect, which the Laplacian is taking care of, and then this Z is just a space-time white noise. So you see that this is a continuum process that for which the Glauber dynamics of the DGFF is a natural discretization. Now, this SPDE has been very well studied, and it admits a stationary solution, which is called the continuum Gaussian free field. Okay. Now, that's not a function exactly. It's only well defined as a distribution because the solution isn't so regular, so you can only integrate against it. But it can be obtained, for instance, also separately by taking the discrete Gaussian free field and taking a limit in an appropriate sense. Okay. So for me, the Glauber dynamics of the DGFF is kind of a canonical pre-limiting object for this well-studied stochastic PDE. So a canonical, discretized object one can study. Now, these kinds of processes have been studied, pretty extensively, and in dimension 2 or dimensions 1 and 2 fall under the name of the Edward Wilkinson universality class for random curves, random surfaces, which have a competition between 1, a local smoothing force, which is what the Laplacian is doing, and 2, a kind of white noise space-time independent stochasticity, okay, additively. And so generally it's thought that this universality class encompasses a wide array of random curve and random surface models which are evolving in time via these, 1 and 2 here, and they tend to exhibit GFF-like fluctuations. So by that, I mean, for instance, in dimension 2, logarithmic variance, and one would expect that there's some kind of a qualitative, at least, universality in their dynamical evolutions. Okay. So I'll give some examples of random curves and surfaces that fall into this universality class now. So in dimension 1, a few canonical examples are, firstly, the height function associated to the symmetric exclusion process. So, or alternatively, so 1 and 2 are actually equivalent, a ±1 random walk bridge. So that's depicted here. And the correspondence between the exclusion process and the random walk bridge is if you have occupied particles and empty particles, then you can just say you go up whenever you have an occupied particle and down whenever you have an unoccupied particle, for instance. And then transitions of the Markov process associated to the exclusion process correspond to what I'm calling a corner flip dynamic. So when you have a corner here, it can flip to this if this particle moves there. Okay. So this gives you kind of a Bernoulli random walk and a natural Markov process over those, and that's depicted here. A generalized version of interfaces now no longer necessarily taking integer values is grad phi interfaces. So these are, I penalize, so whereas the Gaussian free field was doing a L2 penalty on the gradient of the heights, you can do a LP penalty or some convex function of the absolute value of the gradients, and that can give you maybe random surfaces that look like this. And a more statistical physics example is the interface one obtains from the Ising model in 2 dimensions. So when you look at an Ising model in 2 dimensions and say you put plus boundary condition somewhere and minus boundary condition somewhere else, the interface is now a 1-dimensional random curve. It's 1 dimension lower, and that behaves like a Brownian bridge in a scaling limit. So all of these admit Brownian bridge scaling limits, and their dynamics should in some sense be universal, but that's not really confirmed. Okay. In dimension 2,
in the first case, you mean supercritical? Yes, I guess supercritical is the model, right?
Low temperatures.
Yeah, low temperature.
Yeah, that's right. Okay, so in dimension 2, the kinds of random surfaces one thinks about. So I think the most canonical random surface in dimension 2 is the discrete Gaussian free field. A generalization of that, again, is this kind of grad phi interface where you have instead of, so whereas the discrete Gaussian free field had e to the minus this kind of a penalty, this is like a 2 norm, let's say, this grad phi interface has a penalty of the form maybe e to the minus some convex function of this. Okay. Other possibilities are the height function of a dimer model, if you know what the dimer model is. Alternatively, there are many approximations to a 3D Ising interface now. So again, you take a 3D Ising model, you put the relevant boundary conditions at low temperatures, and then the interface becomes a 2-dimensional random surface. And so there are things like what's called the solid-on-solid model, which is depicted here, which only takes integer values. So that's the analog of like an integer valued random surface, which has Gaussian free field type fluctuations. So there's again a whole host of random surfaces that are supposed to fall into this Edwards-Wilkinson universality class. And these should, at least in some sense, have log n fluctuations and be log correlated. So at stationarity, these are the hallmarks of this kind of universality class. And especially in dimension 2, a lot less is understood about how general is this actual universality. Okay. So in particular, the convergence to the Gaussian free field, or the fact that things behave like a Gaussian free field, is only known in the dimer case here, not in 4 and 5. Okay. So with that, I'm going to now transition over to talking about dynamics. So the relevant question when we're okay, there. So I'm going to transition to talking about dynamics. So the relevant question that we're interested in, for instance, is what's the behavior of an off equilibrium dynamics for the model that we described. So take the Glauber dynamics for the discrete Gaussian free field, start it far from equilibrium in some sense, and look at what is the behavior of it as it converges to equilibrium and how long does it take to converge to equilibrium. So this question of how long does it take can be quantified in what's known as a mixing time. And that's asking maximizing over initial conditions. And I'm going to add the constraint that the initial conditions say have maximum value less than n, because if we let the initial conditions be as high as we want, then the mixing time can take arbitrarily large if you're very high up. So we need to put some bound on it. This bound of n is in analogy with a lot of the integer valued random surface models I described in the last slide, which can only take maximum height. And then you look at the total variation distance between the law of the dynamics and the stationary measure at time t. And this quantity we'll call dTV of a time t. So this is roughly the worst case total variation from stationarity at time t. And a Markov chain is said to have cutoff at time tn with window an if essentially there's a sharp drop off in the total variation distance from 1 to 0 within a window an of tn. So what I've drawn here is this is on this axis is this dTV of t, and you see that there's a window that's of size an, which is little o of the true mixing time, where I go from total variation distance almost 1 to total variation distance almost 0. Okay. This is a very extensively studied phenomenon in the study of Markov chains, dating back to work of Algis and Diaconis in the 90s. It's believed to be a general phenomenon that happens for fast mixing Markov chains, or Markov chains where the spectral gap is of a different order than the mixing time. So if you know the background there, then you'd understand that this is kind of supposed to be the best possible type of result one can obtain for a Markov process that has fast mixing in some sense. Okay. So just some background on what's known about mixing times for the random surfaces we described. Work of Wilson in 2004 showed that the random curves, so I'll focus first on random curves in dimension 1, showed that many of the random curve models that I described, and in particular, for instance, the exclusion process one or the DGFF. Sorry, somebody asked, what is the size of the box for the DGFF? Yes, the size of the box is n. So I'm looking at a box of size n by n by n, or n by n, and I'm also taking my maximum initialization to be of order n. Okay. So returning to Wilson in 2004 showed that the mixing time of these random curve models is of order n squared log n. And the way one obtains that is with the following key insight, that the expected value of the height function evolves by the discrete heat equation, now no longer stochastic, just the deterministic heat equation, okay? And one sees that just because the white noise term drops out in the expectation, so you just have a Laplacian acting on the surface, okay? Now, one can study this discrete, now PDE instead of SPDE, and see that it kind of follows this behavior where if I start from a maximum initial profile, I drop like this, and eventually, once in expectation, my height is very close to the tip, is very small, let's say order 1 or even microscopic, then you can couple the stochasticity quickly and are therefore mixed, okay? So one doesn't get the precise constant in front of the n squared log n from this argument, but it's a fairly general argument for all of these Edwards-Wilkinson types of dynamics where in expectation, the evolution is just a Laplacian acting on the surface. Okay. Things kind of stayed this way, with this being the state of the art until work of Lacan, which showed cutoff for the exclusion process at exactly, so identified exactly this constant 1 over pi squared in front of the n squared log n, okay? And the way you should think about this is this 1 over pi squared is the time for the expectation to get on order square root n in dimension 1. So the expected height of the interface to get of order square root n, then the fluctuations are able to wash away the expectation, and therefore you can couple. Oh, for some reason, there's a delay in the slides. There we go. Okay. So with this work, it was understood that the time to equilibrate is exactly 1 over pi squared n squared log n, and actually the window is of size of n squared, so this is the window size. Later work, there's been a lot of later work using similar arguments, for instance, for the exclusion process on the circle instead of on the line segment with 0 boundary conditions. And then more very recently, Caputo, Labbe, and Lacroix established a kind of universality of this cutoff phenomenon for grad phi type interfaces. So remember, the discrete Gaussian free field in dimension 1 fits into this setting by taking the potential to be a quadratic one on the gradient, okay? But generally, they showed that for all of these kinds of grad phi type interfaces in dimension 1, you have cutoff exactly at 1 over pi squared n squared log n. So the cutoff value is the exact same time. And again, this 1 over pi squared comes from the expected height getting on the same order as the fluctuation. So then the fluctuations can wash the bias away. Okay. In dimension 2, a lot less is known. So for the discrete Gaussian free field specifically, the arguments of Wilson basically generalize. So you still have this fact that in expectation, your interface looks like it's just following a PDE evolution or a discrete PDE. And with a little work, you can get from that you have this order n squared log n mixing time and order n squared relaxation time or inverse spectral gap. But as soon as you move beyond the DGFF, so let me first say, also so we know the order of the mixing time, but we don't know the exact constant. And another thing that that has been shown for this dynamics is, at least if you look at like a suitably renormalized version of it. So if I scale space by n inverse, which is the macroscopic scaling, and time by it, I look at order n squared times, and that's the scaling at which I look. I get actually a convergence to a nonlinear, to a deterministic PDE, which is known as the mean curvature flow. Okay, and so here I've shown what that looks like. Again, you kind of have this, you have a surface evolution again at a macroscopic scale, ignoring the fluctuations, that's evolving kind of according to minimizing a surface tension and just shrinking globally like that. Okay. However, this does not tell us anything. This doesn't tell us anything about the actual mixing time and the time it takes to mix, because that requires a more refined understanding of how long does it take for the fluctuation field here to mix. Okay, so you need all of the fluctuations to look Gaussian free field like, as well as this kind of global behavior to get a sharp mixing time result. Beyond the Gaussian free field case, things are even worse. So in dimensions bigger than 1, the integer effects of, the solid on solid model or an integer valued discrete Gaussian free field, things like that, actually break down the argument of Wilson. So now the integer effects make it so that in expectation, it's no longer a Laplacian that's governing your evolution. There might be some rounding errors. And those rounding errors are catastrophic for the estimate because maybe they're biased in some direction. Okay. Schmidt and Boudinot recently showed that we're able to show that for the integer valued free field, so that's just the discrete Gaussian free field, but you also constrain it to only take integer valued heights. They showed that the spectral gap is still of order n squared, and the inverse spectral gap is still of order n squared. And for the solid on solid and easing interfaces, no sub-exponential bounds are even known, okay? So the situation in this dimension bigger than 2 setting is much worse than the dimension 1 setting. And our hope is to just take the simplest version of the dynamics in dimension at least 2 for random surfaces, which is the discrete Gaussian free field, and prove cutoff, okay? So indeed, that's, sorry. Do you see what slide do you see here?
There are no numbers in the slide, so the slide I
Is
see
it
is the one
still
with
this known
hydrodynamic
result?
limit and integer values random surfaces.
Okay, 1 second. For some reason, it's not. When I change the slide on my iPad, it's not changing on the screen. So let me connect a cable or something. Sorry, technical difficulties. Okay. So we were here, now we're here. Okay, so the main result that I want to talk about is that for any dimension bigger than 1, so including in particular dimension 2 and higher, the Glauber dynamics for the DGFF with these kinds of 0 boundary conditions has cutoff at d over pi squared n squared log n, and with an order n squared window. Okay, so as you can see, if you plug in dimension 1, you recover exactly the results of this of what's known for dimension 1 for other random curve models and their cutoff. And in dimensions bigger than or equal to 2, this now is no longer the time it takes for the average of the height to get to the order root n. It's now the time it takes for the average to be of order something dimension dependent, which is going to compete with variance such that the fluctuations can wash it away. Okay. So the main tool for showing this is a kind of backwards random walk representation of the dynamics. So we uncover some kind of exactly solvable structure to the dynamics where, so we fix a Poisson noise P, and this Poisson noise is going to be the clock rings at all of the vertices. So if you recall, I was saying you start your Glauber dynamics H of 0 at time 0, and we were running forwards in time. And whenever we encountered one of these x's, we'd update the height at that vertex according to the average of its neighbors plus an independent Gaussian, right? So that's the Glauber dynamics moves forward in time, and you get some surface up here, H of t. Okay, now take that same Poisson noise and freeze it. So let's fix a realization of the Poisson noise. And what we're going to do is we're going to start a backwards random walk from this point. This is x up here, let's say. So from a point x at time t. And the backwards random walk is defined as follows. It goes back in time until it hits an x, so one of these clock rings. And when it hits an x, it just jumps uniformly to one of its neighbors. Okay, so it's a random walk in this Poisson noise field in the sense that as soon as it hits a clock ring, it's going to jump to a neighbor. Okay. Now, one can see that because there are no clock rings on the boundary, so this is this here and this here are partial lambda n. And remember, this is a 1D picture, but in reality, in dimension 2, for instance, this lambda n goes backward. This is like, and there's kind of lines down all over, and then this is your boundary. So whenever your random walk hits the boundary, now there's no more clock rings for it to see, and so it's going to be absorbed for all time. So it has the same effect of absorbing the boundary by just not putting red tick marks or clock rings on the boundary sites. Okay, so that's what this green random walk is doing, is it hits the boundary and then it's never going to move again, okay? Now, the random walk representation of the dynamics is an exact equality between two processes. So first, let's assign every one of these little clock rings an IID Gaussian, standard Gaussian random variable. So if this is the point P in this Poisson field, then I give it the random variable Z sub P, okay? The exact equality is conditionally on this P. So this is the dynamics conditional on P. The H of xt is exactly equal to the expectation over just the jumps of the random walk of the initial height profile evaluated on, so this S0xb, S is the random walk, and at time 0. So remember, we start at time t and go backwards. So at time 0 is after a time negative t of running it. You just evaluate the initial height profile. Now, if it's hit the boundary before then, this contributes nothing because the initial profile takes value 0 on the boundary. So it only contributes in the case of this red random walk, for instance, where it gives you whatever h of y was here, for instance, h0 y. So that's the first term. And the second term is just a sum of all of the Gaussians that the random walk encountered. So you think of it as average over random walk trajectories of, as it goes along this, this Poisson field, every time it hit the ring, it just collects a IID Gaussian, okay? And the IID Gaussians are assigned to the clock rings. And then once it reaches time 0, it just collects whatever was the initial value at the point it hits time 0 at, okay? And again, this expectation is over the random walk jumps. And these Z sub P's are basically the same as the Gaussians that are coming up in the evolution when you're using the Laplacian plus an IID Gaussian. Okay, so there's a bijection between the Gaussians on the right and the Gaussians on the left. So this is an equality. Okay. As a corollary of this, we see that conditionally on any Poisson noise field, the law of the dynamics is Gaussian. Okay. So if I freeze the clock rings, the sequence of all the clock rings, my dynamics is actually going to be Gaussian for all time.
So just to make sure that I understand well, so your process S, because of the time reversal, it's not a random walk because of this absorption rule. Because if it starts at 0, the time at which it leaves 0 is non-Markovian, right?
In the other direction, you're saying, in positive direction? It's not a reversible process at all, because when it hits the boundary, but going backwards, it is Markov.
Okay, it's Markov, but
not
only in the
reversible.
backward direction and not in the forward direction.
Not in the forward direction, exactly. Yeah. So it's just to draw a realization. I start here. This is, let's say, some point y. This will be SYP of t minus s. Okay, and so s is going, this is s. And then I hit a red thing and I jumped uniformly to a neighbor. Then I go down, I hit another red one. I go down, I hit the next red guy, I jump again to a uniform right neighbor, and this process continues. Does that make sense? Okay. So as a corollary of this, we see immediately that the process is Gaussian because it's expressible as a linear transformation of IID Gaussians. So your IID Gaussians are these Z sub P's, and this is clearly a linear operator if you just think about it for a bit. Okay. So that's kind of nice because that gives us access to kind of exact things that one can do with Gaussians that we don't have access to otherwise. In particular, we can compute the mean and the variance of, and the covariance of the dynamics at any fixed point in time, okay? So the mean, one sees, these guys are mean 0, all of these Gaussians. So the mean of the process is simply the contribution coming from the first term, okay? The first term doesn't have any z's in it, so it's just the expectation over the random walk trajectory of the initial data evaluated on where you hit at time 0. So you run a random walk backwards in time from t to 0, you hit a random point, and you average over the random walk trajectory. That's the expectation for the function, okay? One way to think about this is if your initial height profile, so if h of 0 is identically n, for instance, that's the maximal kind of initialization, then all of these are n, n. Then this will just be expectation HP is just equal to n times the probability of survival of the walk. Or phrased another way, maybe the probability that the walk is not in the boundary. Because if it's not in the boundary, you pick up the initial value n, and if it's in the boundary, you just pick up a 0. Okay, so this relates it to a survival probability of a random walk. For the covariance, if you think about it a little, one sees that the covariance is given to you by the intersection time, where time is measured by number of clock rings. Okay, so the number of clock rings shared by the random walk started at x and the random walk started at y. Okay, so this expectation, again, it's all of these expectations are over the random walk trajectory. So here I've drawn a picture. This is x and this is y, and you see that they share only this one clock ring. Okay, so for them, but then you average over all random walk trajectories. Okay, the key thing to notice here is that the Poisson field is shared between the two. So now these aren't anymore independent random walks. They're, how often they jump and things are kind of depend on one another and also spatially dependent, okay? But this gives you an exact form in terms of random walks through this Poisson field of the covariance structure of the dynamics itself, okay? Now, one can see if with a little thought that if I extended this process down to infinity, or minus infinity, I guess, because of stationarity of the Gaussian free field measure, it has to be the case that, this limit covariance is the Green's function. So the covariance of the Gaussian free field itself, okay? And so by that calculation, we can give this other form of the covariance, which is you're always smaller than the Green's function. And the difference between the covariance of, so this is the dynamics at time t, the difference between its covariance and the Green's function, or the stationary covariance, is essentially the covariance evaluated at two random points, which are the points at which you hit at which the two random walks are at time 0. Okay, and then averaged over all random walk trajectories, or all pairs of random walk trajectories. So this is nice. So the covariance of the process increases to the free field's covariance. And already from that, you can understand some things, which are, for instance, that the fluctuation field has always variance at most log n in dimension 2. So it's always pretty smooth as it's decreasing, and you can bound gradients and things, or maxima and things like that. Okay. So how we're going to use this is using a exact characterization of the total variation between two Gaussians. So again, because they're Gaussians, we have access to nice expressions, exact expressions. And so here's an expression for the total variation distance between two Gaussians in height dimensions. Okay, so there is no dimension dependence on the right. That's the key point, because if there were, that would kill whatever. But what you have is that the total variation between a mean 0 Gaussian with covariance sigma 1. So this, think about this as the GFF because it's mean 0. And so this guy will be a normal 0 Green's function essentially. And this will be our height, h of t. Their difference is given to you by two terms. One is roughly a mean quantity. So it's discerning the contribution from the difference in the means. And one has no mean term and is only discerning the contribution coming from the covariances to the total variation distance. Okay. So in our context, the mean mu2, yeah.
I have a question. So in this theorem, there is an asymptotic relation. So it's, yeah, in which sense is it an asymptotic? What do you need some assumption over, okay, I don't know, the size of your sets?
So in the sense that this is at most some, I don't know, 100 and at least 1 over 100 times the same quantity.
Okay, so it's uniform over all mu and sigma.
Uniform over mu, sigma, and the dimension.
Yeah, okay, thanks.
Exactly. So it's a really sharp bound on the total variation between two Gaussians. Okay, so so for us, the mean is exactly the mean of the height that we were saying. So it's roughly you can think of it as n times the probability of survival of the random walk, started from a point x. The first sigma is just the Green's function. And the second sigma is this Green's function minus this residual average of Green's functions, okay, evaluated on where the random walk hits at time 0. Okay. The point just being there's nice expressions for all of these quantities. Okay. Now I'm gonna just try and see. So I want to just try and parse this second term a little. The first one is roughly, it's almost mu to mu2, ignoring the role of this Green's function on the bottom. And so, you know, this is basically the size of the mean vector in some 2 norm. Okay, so that's kind of innocuous. It makes sense that that should appear in a total variation. Maybe divided by a norm of G is how you should think of it, right? On the right, though, I want to just reinterpret this term, which is the fluctuation term or the covariance term in the difference. And so if I just write sigma 1 inverse sigma 2 minus I, you see that I get G inverse times G minus expectation G of X naught SP. X naught P. Okay, so this gives me, and then minus identity. These two here cancel out with the identity, right? And so I'm just left with G inverse, and then this expectation, okay? Now the expectation I can think of as take the heat kernel for the random walk. So that's what I'm gonna call this HT. This is the probability that if you started at X, if you start at X, you are at Y after a negative time of T, okay? So it's just the heat kernel for the random walk, killed at the boundary. And I can write it as G inverse H, G, H transpose, okay? So this is a nice kind of expression for the second term here. And we need to understand the 2 norm or the Frobenius norm of this matrix, okay? The first guy, remember I said that the mu can be roughly written in terms of the probability of survival for the walk, which is like a sum of this HT. Okay. So, sorry, okay. There. So I can express things in terms of this heat kernel pretty explicitly. And so this reduces the analysis of the mixing time and proving cutoff bounds and things like that to understanding fairly precise asymptotics about the heat kernel of the backwards random walk in this Poisson field, okay? Now, let me just show a couple of the key ingredients that one would need to estimate for this kind of a random walk process. So what we need to say is, with high probability over the randomness of the clock rings, so over the Poisson field, for the mean, we need to control this probability that by time -t, my walk hasn't hit the boundary of my box, okay? And so that's just a sum of these heat kernels for the interior. And for the covariance, I need to understand things. So if you recall that G inverse, the inverse of the Green's function, is just the Laplacian, then one sees that for the covariance term, you need to understand two types of quantities. One is kind of Laplacian H, which is differences of the form of like the probability of surviving from X minus the probability of surviving from its neighbor, okay? So how different is the probability of surviving or not hitting the boundary for two neighboring sites? That's basically what the first term is. And the second term is roughly governing quantities like I take an average over a Green's function, where the average is with respect to this heat kernel. So I like run a random walk, I look where it hits, and then I look at the Green's function there. And I look at the expected value I get. So if this were a simple random walk, these are kind of all straightforward quantities on a lattice to compute. But for us, I want to give a warning about the heat kernel in this Poisson noise. So first of all, the trajectory that the walk takes is correlated with the number of jumps taken. So the number of jumps is a kind of Poisson random variable if one doesn't know about anything else, because you can kind of couple it to just exponentials every time you make a jump to see the next clock ring. But the key thing is that the trajectory is correlated to the number of jumps. So you want to use the fact that the number of jumps concentrates well, but it's related to where you actually ended up, okay? For instance, if there's a region that has a lot of clock rings, you're going to move at a faster speed out of that region typically, because you're going to make more jumps in that region. A more concrete example is, let's consider the site with the earliest clock ring. Okay, so that's this guy. This is the one whose clock ring is closest to 0. The probability that the random walk is here at time 0 is 0. There is no chance it can end up there, because if it's coming through here, it's going to jump at that time, and no other clock ring can send it there after that last clock ring. Okay, so whereas the heat kernel for a simple random walk with discrete discrete time is, is fairly well behaved and fairly smooth, except for boundary effects. Here, the clock rings can make it so that some sites you have actually 0 chance of landing at. Okay. Also, sites like this one, where there isn't a clock ring for a while, can have a much larger value of the heat kernel, because a lot more mass is going to be shipped into there and never leave in that last time segment, okay? So at a local scale, the heat kernel can be fairly distorted as compared to the heat kernel for a simple random walk. Luckily, all of the quantities that we were talking about here on this slide are kind of averaged quantities. So let me see, sorry. Yeah, so all the quantities that appear on this slide are averaged quantities in some sense. So you never really need like refined local control on the heat kernel, because if you did, then you would lose some logs or something like that. But because we're generally averaging over, and the Green's function, for instance, is a pretty smooth object, it doesn't matter so much that there's local oscillations as long as things homogenize at global scales, or not global, but maybe like moderate, intermediate sized scales. So let me just give a flavor for a couple of the actual heat kernel estimates we show for this backtracking random walk in the Poisson field. So there's an estimate on the survival probability where we show that it's of the size of, this is the top eigenvalue of the Laplacian on lambda n. And this is its normalized top eigenvector. Okay, so the survival probability decays exponentially in the top eigenvalue of the Laplacian on lambda n. This is kind of a common thing for these kinds of heat equation type of evolutions. But you see that the contribution coming from the fluctuations in the p can be absorbed into a little o of 1 multiplicatively. Okay, so that's not so bad. Another type of estimate one can get is a diffusivity estimate for the backwards random walk. And so what we mean by that is that the random walk in any time t will not move more than root t log n, let's say, started from any site. Okay, let's say for all x. Okay, so the probability that it moves more than a root t log n distance is polynomially decreasing. So this is, again, an estimate that would be obvious in the simple random walk case where you just make discrete time jumps or Poisson jumps. But in the presence of this Poisson field is a little trickier because, like I said, the trajectories are correlated with how many jumps you take, and that can affect the speed with which, or the diffusivity of the random walk itself. Lastly, we need some kinds of heat kernel bounds. So the probability that, sorry, this should be a 0. The probability that after a time of t, the backwards random walk ends up in a set A. Okay, so as I said, for a general set A, let's say it's the vertex which has a long amount of time before its clock ring, this can be problematic because if there's a kind of region with few clock rings, then a lot of mass can get in there and stay there. Okay, and that can distort the heat kernel. So for us, what we look at are mesoscopic scales. So whereas for the simple random walk, what you would hope for here is the size of A over n to the d e to the minus lambda 1t. So this is the probability of even surviving for that time. And then this is saying you're pretty mixed. So it's just the volume of the set, the relative volume of the set to the whole space. Okay, we pay this factor. So you have to enlarge your set by a root n distance. And then if you do that enlargement, then the bound holds. And this enlargement is so that you can smoothen all of these local oscillations in the heat kernel given to you because of the Poisson noise. So this is sufficient, obviously, to treat sets A whose size is larger than root n. Then the enlargement becomes just a constant and it's not so bad. Okay, a constant multiple. Now in dimension 2, the Green's function doesn't oscillate so much on such mesoscopic scales. So we don't need a more refined estimate because the smoothing of the Green, or the smoothness of the Green's function allows you to only care about kind of local averages or mesoscopic averages rather than like single point kernel bounds. Okay, let me just wrap up at this point. So to conclude, so to speak, the proof of cutoff from what we've deduced up to now, you first want to reduce the analysis to flattish initializations. So you can say, for instance, the mean is basically the survival probability. And that's easy because of this exact correspondence, this backwards random walk representation. It kind of isolates the role of the initialization into just the mean part. Then you see that the difference in the means contributes something like this. And each of these mu's we said were like n times probability of survival, which was like an e to the minus lambda 1t. So you get 2 of those. And then you get an n to the d from the size of the vector. Okay. And on the denominator, you have like a n squared coming from the size of this Green's function. That's kind of the amount of time any random walk spends in the whole box before it gets killed, times the same quantity, n to the d plus 2 e to the minus lambda 1t, and then a square root, right? So that's this n to the d over 2 e to the minus lambda 1t if you do the math. And so what that tells you is in order for this to be microscopic, I need t lambda 1 to be log, d over 2 log n, right? So for this quantity, that's the scale at which this quantity kind of varies, okay? And this actually identifies exactly the cutoff location. That's the calculation that one does. And for the covariance term, one can see that using the kinds of bounds we had, you get the same kind of trade-off. Again, so that one's d over 2 and lambda 1t. Here it's n to the d, but twice the same quantity, okay? And so at that time, you've lost everything. You're seeing a transition in the total variation in both terms, okay? So that gives you this cutoff location. And I'll conclude with a couple open questions that might be of interest. So the first one is, can one identify the cutoff profile from this maximal initialization? So what I mean by that is we identified that there's cutoff at this t star n, and it has a window of order n squared. So what if I look at the total variation as a function of the prefactor of the n squared? So that's the scale at which it changes. What does this function look like? And so this has been identified, I think, by Laquan for the exclusion process in dimension 1. So it'd be interesting to understand what this function is in dimension 2, for instance. A second question is, what about the mixing time in the presence of a floor? So suppose you don't allow the Glauber dynamics to make any updates that send its height to be negative. So it always has to be positive. This leads to a kind of well-known entropic repulsion phenomenon for the discrete Gaussian free field. And the repulsion phenomenon is pretty different in dimension 2 than it is in dimension 1. So in dimension 1, it was shown that the process has the same cutoff time, actually. But it's an interesting question to ask, does it have cutoff? Is it still n squared log n? And then, like, is the cutoff time the same in dimension 2, for instance, where the repulsion actually plays a bigger role? And lastly, KPZ is a whole different universality class of random curves and random surfaces. You have an additional term that's in terms of the gradient of the height function. And recently, there's been some work studying the asymmetric exclusion process, or ASEP, and biased card shuffling, and those fall into this KPZ universality class. So in dimension 1, what about KPZ type evolutions in dimension 2? And I'll conclude there. Thank you.
Thank you, Reza. So yes, I have many questions, but I will check for the audience first. So, okay, maybe if you raise your hand, I can.
Or maybe a simple question. You have a guess for this function ds with the profile?
Oh, I don't know enough to guess that. No. In dimension 1, maybe Laquan, Hubert can say knows a bit better than me. Do you have a guess about, like, in dimension 2, what the function should be related to?
I don't know. It depends on the belief. The Poisson, yeah. If the in dimension 1, what you have is that if you look at your the mean decrease exponentially, and the fluctuation part, it's mostly the first Fourier coefficient that counts. So what you're really
the fluctuation should be mixed by then, right? It's just the mean, really.
Yes, and for this reason, what you get is some kind of a Gaussian profile. So I mean, the profile you get is some combination of the Gaussian error function and exponential in T, because your mean it decays exponentially in T.
So probably you should get something similar in dimensions bigger than 1, right?
Yes.
I mean, again, the fluctuations should be mixed by the cutoff point. And so it'll just be governed by the mean term.
Yes, so this is okay. I have a question about these fluctuations getting mixed by the time of cutoff. So in your estimates, yeah, I don't know. It feels kind of magic that the two things mix at the same time, because in dimension.
Well, we can do better. No, we
Okay.
can do better.
Okay.
Yeah, we can't. Using just what we wrote, we can't show that the fluctuations mix in n squared, which should be the truth, without a log n, I think.
Okay.
But we can show that it's a whole different constant log. So it's a much earlier time. Constant
okay,
n squared log n is an earlier time when it's mixed.
Okay. So these things should not depend on the dimension. It should always be of order n squared.
Yeah, the fluctuation,
Okay.
I think, should always be of order n squared, independent of the dimension. I just gave kind of a naive version of the bounds where, so for instance, a bound you can do here is just do Laplacian and then HGH transpose. And this is obviously a bad bound because this Laplacian should decrease this quantity on the right. But if you do this naive bound, this is the bound you'd get.
Okay.
We can do better than that, but not the right n squared.
Okay.
Because of these kind of local things of the Poisson field.
Okay, but yes, in order to get the profile in dimension one, I think the important was to get like 1 minus delta times the cutoff time. So this can be.
Yeah, so we can do that. We can do 1 minus delta. I mean, if you just look at the fluctuations, like, yeah, sorry. I think someone has a question.
There is a question by Federico. You can unmute yourself.
Yes, thanks for the nice talk. I was wondering that you have these hard hit kernel estimates, somehow concentration type of hit kernel estimates, but for the upper bound for the total relation distance, don't you just need a annealed type of hit kernel estimate? So
annealed in the Poisson field, you mean?
Yeah, exactly.
I think so you can, a lot of the estimates, in order to get 1 minus little over 1 probability, you can first average over both both the Poisson and the random walk, and then just do a Markov argument. So that works, for instance, for the survival probability. For some of the other things, one has to be a bit more careful because of this trajectory dependence. But you can, yeah, I mean, a lot of the arguments go through some kind of like averaging over both at the same time or doing some coupling. Okay. That's right.
Okay, thanks.
So I was wondering, it seems that Poisson does not help you anywhere. And some people have looked at Glauber dynamics with a systematic scan of coordinates rather than using a Poisson process. So using your approach, would you also get results in the case where you have a, you just visit your box line by line or in any sequential order? Do your estimate concerning your random walk still persist? Or?
Yeah, that should be, that feels like it should be doable. I mean, the synchronous random walk, that's an even easier case where everyone updates simultaneously. If you had synchronous updates instead of this Poisson.
Yeah, you can, okay.
If you had
updates, you can define synchronous.
Yeah, you can just take the average at the like right before. If you did a discrete time, everything will go through with what we did. If you did systematic, now there's not randomness in but I think you should be able to, I agree. I think you should be able to get the kinds of estimates that you need to do it.
But if now I'm a bit puzzled. If you do synchronous updates, you get the same. It seems that you kind of produce extra noise. You get the same equilibrium measure.
It has definitely the same equilibrium measure, right?
Because if you update one person and then its neighbor, somehow, I don't know, you kind of construct negative correlation. Okay, I should think about it.
But the stationarity of the free field is still stationary, right? Because they're Glauber type updates. So it's like when you do an update, it's just the law of that site conditional on its neighbors. So as long as you have that type of an update, it doesn't matter what your update sequence is. It's still going to be that the GFF is stationary.
Yeah. But I was troubled by the fact does this argument still work when you have? I thought that this was based on the fact that the updates were not simultaneous. I have trouble visually to see that this is really Glauber dynamics when you have simultaneous updates. But maybe it's only my problem. I don't know.
I'm not sure. Are you saying the synchronous case or the systematic scan case? Which one?
No, the synchronous case.
Oh, in the synchronous case. Okay, sorry,
Yeah,
I was
wondering if you
yeah.
don't produce, by synchronizing the updates, you don't produce some extra noise. Actually,
I don't think so, but I'm not sure. Yeah.
Maybe one thing that I found at first quite surprising in the result is that somehow the time you find for the cutoff, it really does not depend on the dimension. In particular, in dimension 2, you don't see the effect of this log.
Right. Yeah,
okay.
the log n doesn't show up. So the key thing there is that the dimension. So I was saying that you roughly want to get down to the order of the fluctuation, but it's not the like 1 point variance that you want to get down in order. It's like an averaged green function. So what's relevant is not, you don't want to get down to the size of the fluctuation at a single point, but rather how big is the fluctuation if you pick 2 points at random and then evaluated the covariance between those. So in dimension 2, that's order 1. And in dimension 3 and higher, that's decaying as n to the d as n to the 2 minus d. And so that is the fluctuation amount that's governing where you want to get your mean to. Whereas, yeah, initially when we were thinking about it, we thought, okay, you probably need to get to order root log or something, and then the fluctuations of the GFF will take over. But actually, you need to get lower than that.
Yeah, so I was wondering, do you get any result if you look at not the time for the whole system to get? Can you get results if you're not looking at the distribution of the whole field, but just the field at one coordinate or at on a mesoscopic box?
Yeah, I mean that the way we give our lower bound actually is basically that rather than this total variation equation. But I think if you looked at 1 point, it should be pretty straightforward, and it should mix quicker. It should only have to get to order the order of the variance of the height, or square root of the variance maybe, rather than the average of the Green's function.
Yeah,
so
okay.
in dimension 2, you only need to get to root log. You only need to get to root log, and then of course the variance is going to wash the difference in the means away. But kind of on a more global scale, what's relevant is getting to like pick 2 points at random. What's GXY, that scale?
Oh, I see. Okay,
yeah, so the local mixing is a different time, whereas in dimension 1, you locally mix at the same time scale as globally mix. In dimensions 2 and higher, you locally mix much faster than you globally mix.
Okay, thanks. Do we have more questions? I don't see any hands. Okay, so Reza, thank you very much again for your
Thank you.
very nice talk.
Thank you.
And yeah, hope to see you in person in Brazil someday.
Yeah, hopefully. Yeah, thanks so much. Good chatting. Bye.
Bye.